So
Absolutely.
the first talk is about scripting in Virtual Cell. We have a can you go to the top of the thing? Here's a we put a lot of effort into this very recently. So for years, people have asked, is there scripting available, or can I programmatically, make alterations or workflows in Virtual Cell? Now, traditionally, it was very difficult. We now have a Python package called PyVCell. It allows for local scripting of spatial simulations and local edits to models. And this is brand new stuff where it'll get better all the time. But we had to pull a lot of technologies together. Virtual Cell is built on Java. Java and Python don't speak nicely together. So there was some thing involved in that. So essentially, PyVCell is local scripting. It also embeds a client that allows you to talk to the vCell remote APIs, either as yourself logged in using your browser or anonymously. Um, so maybe I'll skip right through this. Essentially, you can use virtual cell models or SPML spatial models. Here, this is only for PDE's spatial modeling, even though virtual cell can do other things. This is what the focus of this work is. We can run the simulations locally, analyze the simulations locally, visualize simulations locally, script it, loop it, do whatever you want with it, right? Why don't I let Alex take over since we have so little time? Alex, just do a quick run through of the what we have.
Sure. So this is a demo that is actually available in the PyVCell repository within the Virtual Cell organization on GitHub, just for everyone's information. So the package is available on the Python package index, just with a quick install of pip install PyVCell. Highly recommend that you use some sort of environment manager to kind of handle the dependencies as best practice. And this just adds example files to the demo that we have here, so you can do everything right within this demo, just for everyone's information as well. So in a first simple example, we start with an SBML model and create a simulation instance with the model instantiated by this model file. And we create the SBML spatial simulation instance, and we run that simulation, which returns a result instance that is a post-processing class that has within it many analyzation and visualization methods. So in just this first simple example, I've included the species concentrations over time. And we'll get a little more into how the channels are exposed in that. And actually, just as a kind of side note, the result class also has access to VTK visualization and the file format in general. So I'm just showing here that we can create the result has a VTK data attribute that can be queried, and we can actually generate fully formed VTK files from the output data of our simulation. So that's just a very simple example to start. And just in the interest of time, I'll move along. Here in a second example, we have a more complex declaration of our model, and we actually start from scratch in this case. And we're actually going to, instead of SBML, we're going to use the VCML format for this. So we have our imports. We start with an empty model and give it a name, and then we instantiate a biomodel instance with that empty model. And then, just as you might expect, we add our sort of components to the model. So we have our compartments that we've added in this example. We add species, which has a reference to the compartment in this case. We add a reaction, and as you can see, the keyword arguments are pretty self-explanatory here. It makes it easy to just kind of configure this and hook them together. We defined a geometry, and then we added the components to the geometry here, a cell membrane, and notice that we've defined its origin and its extent and the number of dimensions. And just as usual, we create a new application instance, which ends up being an attribute of the biomodel, the previously formed biomodel. Then we just have to add everything that we defined previously to that application. So we map our compartments, and we have specifying a domain. We map our species and the diffusion coefficient, for example, and as we can see here, the boundary conditions. We map our reactions to the app, so we're adding all of these components to the application. Then we have a simulation configuration instance in this simulation object, which specifies a duration, a time step, and a mesh size. And then we add that simulation to the application. And then here we can create the document. There are a few high-level readers and writers that can convert this into a VCML document, and we're just printing that here. So as you can see, all of the components that we've configured have been appropriately defined here. And just as a third example, we're going to extend that, and we're going to just take that model that we just created and run the same kind of workflow as the first example, but with this VCML simulation and model. So we create a VCML spatial model using the biomodel instance that we created previously. And we want to specify the simulation name to run when we call run. So this is available as an attribute of the original simulation, but we just wanted to show that it's found within the application that we've created. And so there's a list of applications, a list of simulations, and then that has a name. We create the VCML simulation spatial object, and we run it as usual. And I just wanted to show a few of the other plotting methods that are available. So we can plot a 2D slice of the 3D data by specifying one of the channel names, in this case, just picking S0. And we have to specify a Z index for the 2D representation. And this is what we have. And this is all using matplotlib, and it using the result .plotter attribute. And then we have that same slice at that same time point, but in 3 dimensions. And I just wanted to touch here that PyVCell evaluates functions in parallel using NumPy and num expression with NumPy arrays for each symbol in an expression, including X, Y, Z, and T, which can also be visualized. So this is just for kind of demonstration purposes that we can visualize the X symbol and the region mask, just as a way to show how the data is parsed for plotting. And just for convenience, I've made that entire custom model workflow available as a function within this demo, so you can just edit the lines as you see fit. for your use case, then we want to make a document. So that's been a little bit about what our current state is. We also are able to animate the 3D plots that we've created, and we'll be adding more tutorials and demos in the future so that you can see that. So just to touch on our goals for the future, we and there are several people working on PyVCell. And so some of our goals are that we want to achieve standalone modeling and simulation in PyVCell, because right now PyVCell transparently calls the VCell API to pre-process simulations. And we want to embed selected VCell algorithms as a PyVCell native Python package so that, again, we don't have to have that layer in between. We are definitely want to expand our plotting capabilities and customization, and actually even be able to have Jupyter widgets and various clients that we can create from this tooling. We want to add even more modeling support and validation and error reporting so we can really have a very good quality set of models. And to expand our VTK capabilities, this is a great format that is used in lots of different scopes. So we want to be able to expand that beyond just plotting, beyond just the export of the document. Of course, we want to improve the validation and just general reproducibility and usability of our spatial models in VCML and SBML. And because we can parameterize our simulation and our model and are getting closer to a low-level interaction, so to say, we want to be able to expose the VCell spatial simulations as, for example, use in other frameworks. So, for example, the compositional simulation framework Vivarium, for which performs multi-scale co-simulation. So we want to be able to incorporate that and expose what we need to expose and don't what we don't want to. And I've made the PyVCell repository available as a link here, so please feel free to check out the content and have fun with the demos. And we'd love to kind of hear your thoughts, of course, as you use it. And just as some final acknowledgements, there are many to acknowledge, and there's I'm new in relativity to this project. This, of course, has been an amazing project, and there's not enough to thank. There's not enough time to thank everyone, but I just wanted to acknowledge the current VCell developers: Dan, Ezekiel, Logan, myself, and Jim. So that is it for me. Just in the interest of time, I'll stop sharing and